We will now continue our study of capacitance by looking at the role played by the dielectric in determining the capacitance of the capacitor, and then we will look at how we can produce different values of capacitances by suitably combining capacitors either in series or in parallel. Let's start by looking at the role played by the dielectric in determining the capacitance of a capacitor. Well, consider a capacitor that is charged with one plate positive and the other negative, separated by air between them. This is a capacitor where one plate is charged positively and the other plate charged negatively. Obviously, there is an electric field in between the two plates. Alright, tell me, what is that electric field equal to? What is the equation for the electric field in between two parallel plates, one charged positive and the other charged negative? It is sigma over epsilon naught, where sigma is the charge density on the plates. Alright, the electric field between the two plates, we are now going to represent it by E0. Now that means this is the initial electric field before we place a dielectric. At the moment you have air between the capacitor plates. Now, what happens when a dielectric medium is introduced between the plates? Let's introduce a dielectric and see what happens. Well, I have now placed a dielectric in between the two plates, and see what happens. Although there are no free charges in the dielectric, displacement of positive and negative molecular charges occur in the dielectric near the capacitance. You see, there are no free charges, so that charges can move, so that polarization can happen. But in the dielectric, with atoms and molecules near the positive charge, will orient in such a way that the negative charges will be facing the positive plate and the other end will be facing the other way. Similarly, the end of the dielectric facing the negative, there will be positive charges aligning at this end and negative on the other end. So these are called bound charges. The charges that appear on the dielectric, they are not free to move. Therefore, we call them bound charges. They cannot move about. So, here you have the negative charges appearing on the side of the dielectric that is close to the positive plate, and positive charges appearing on the side of the dielectric that is close to the negative charges. What do you call these charges? The bound charges. Well, these bound charges are now going to produce an electric field directed in the opposite direction as that of E0. Remember, before the dielectric is placed there, the electric field was from the positive plate to the negative plate. When the dielectric is introduced, these bound charges are going to produce an electric field in the opposite direction. These bound charges produce an electric field E' that opposes E0. Now, here I have represented that E' by these yellow lines. This is the E', that means the electric field produced by the bound charges. Now, therefore, what is now the net field in between the capacitor plates? There is an original field E0 caused by the charges on the capacitor plates. Now, after the dielectric is introduced, the bound charges on the dielectric produces an electric field E' that opposes the original field E0. That is our E0. The net field E between the capacitor plates now will be, what will that be? Will be E0 minus E prime. That will be the net field now between the capacitor plates. The net field E is related to kappa. Now, how is the net field related to kappa? E equal to E0 divided by kappa. That means if kappa is very large, this resultant field will be small. And that is how it influences the capacitance of the capacitor. Now, if kappa is 1, then the net field and the original field will be the same. In other words, there will be no E prime. But if kappa is 2, then the net field E will be half of the original field. And if kappa is 3, then the net field will be 1/3 of the original field. Suppose sigma B represent the bound charge. You see, bound charges are the charges on the dielectric. If sigma B represent the bound charge density and sigma F represent the free charge density, well, the free charges are on the capacitor plates. So sigma F is the surface charge density on the capacitor plates. Sigma B is the charge density on the dielectric, the bound charge density. Then we can say E0. That means the electric field between the capacitor plates before the dielectric is introduced is sigma F divided by epsilon naught. I hope you remember that equation. The electric field between two parallel plates is sigma over epsilon naught. So E0 is caused by the free charges. Therefore, that will be sigma F divided by epsilon naught. And E prime, the electric field caused by the bound charges, will be sigma B divided by epsilon naught. Now, let's do a problem. Two parallel plates have charges Q and negative Q. When the space between the plates is devoid of matter, well, that is free space, the electric field is 2.5 times 10 to the 5 volt per meter. When the space is filled with a certain dielectric, the field is reduced to 1.2 times 10 to the 5 volt. Now, you can see this is E0. Is that right? The original field. Now, what is this? Is it E prime or E? Well, when the dielectric is introduced, the field is reduced to, that is the net field, which is E0 minus E prime. It is reduced to 1.2 times 10 to the 5 volt per meter. What is the dielectric constant of the dielectric? If Q equal to 10 nanocoulomb, what is the area of the plates? What is the total induced charge on either side of the dielectric? In other words, what is the total bound charges? Okay, let's see what is given. You are given E0. E0 is 2.5 times 10 to the 5 volt per meter. You are given E. E equal to 1.2 times 10 to the 5. What does E represent? The net field E0 minus E prime. QF, the free charges on the capacitor plates, is 10 nanocoulomb. And E equal to E0 minus E prime. You know E, we know E0, therefore we can find E prime. Therefore E prime, what does E prime represent? E prime is the electric field within the dielectric, the field produced by the bound charges. So E prime is E0 minus E. That will be 2.5 times 10 to the 5 minus 1.2 times 10 to the 5. And that is 1.3 times 10 to the 5 volt per meter is the electric field due to the bound charges. Now we need to find the dielectric constant of the dielectric. Now can you recall an equation for that? Well, E, the net field, equal to E0 divided by K. Now we know the net field, we know the original field, and therefore kappa equal to E0 divided by E, and that will be 2.5 times 10 to the 5 divided by 1.2 multiplied by 10 to the 5, and that will be 2.08 is the value of the dielectric constant. Okay, what's the next question we need to answer? If Q equal to 10 nanocoulomb, we have that is the free charges. What is the area of the plates? Well, we have E0 equal to sigma F over epsilon naught. That will be sigma F is the charge density of the free charges on the capacitor plates, and that will be the total charge on the capacitor plates divided by the area of the capacitor plates. So I replace sigma F by QF divided by A, and so E0 equal to QF divided by A divided by epsilon naught, and this A will come to the denominator. That will be QF divided by A epsilon naught. Now we have E0, we have QF, we have epsilon naught. Therefore we can find the area of the capacitor plates. Well, area equal to QF divided by E0 epsilon naught. Q0 is 10 to the negative 8 coulomb, 10 nanocoulomb, and E0 is 2.5 times 10 to the 5 volt per meter, and of course epsilon naught. And that gives me the area of the capacitor plates is 0.0045 meter square. Well, we need to find we found the area of the plates. What else do we need to find? What is the total induced charge on either side of the dielectric? Well, we know that E prime equal to sigma B divided by epsilon naught. E prime is the electric field inside the dielectric caused by the bound charges. So E prime equal to the bound charge density divided by epsilon naught, and the bound charge density is the amount of charge, the amount of bound charge, that means the amount of induced charge in the dielectric, QB divided by A over epsilon naught, and that A will come down. And do we know A? Yes, we know A. We calculated that in the previous slide. Now therefore QB equal to E prime A epsilon naught. We calculated A. A is 0.0045 meter square. So E prime is given to be 1.3 times 10 to the 5, and this is our area, and this is epsilon naught. And therefore QB, the bound charges on the dielectric, is 5.75 times 10 to the negative 9, and that is the total induced charge on either side of the dielectric, and that will be 5.75 nanocoulomb. Okay, we will now talk about capacitors